Hi students, so this is the first MCQ in magnetic effects of electric current. A horizontal overhead power line carries a current of 90 ampere flowing from east to west direction. What are the magnitude and direction of the magnetic field due to the current at a distance 1.5 meter below the power line? So imagine there is a power line like this. The current is flowing from east towards west direction. 90 ampere current is flowing. So at a distance 1.5 meter, you choose a point P and find the magnetic field. Very simple only. Now current is flowing from east to west. So I will take this is a straight wire and this is east and this is west. So the current of 90 ampere is flowing from east to west. Now I will choose a point P. So this is a point P which is at a distance of 1.5 meter. So this distance is 1.5 meter. So what is the magnetic field at this point? First magnitude we will find out. So magnitude of the field B is now equal to mu naught into current I divided by 2 pi into d. This is the standard expression, isn't it? Now I am going to multiply the numerator and the denominator by 2 so that this also can be written as, this also can be written as B equal to mu naught divided by 4 pi into 2i divided by d. Because this mu naught by 4 pi is having a standard value. So mu naught is 4 pi into 10 power minus 7. So mu naught by 4 pi means it must be 10 power minus 7. That is why I am multiplying and dividing by 2. So now the new value I am going to write here. So B is now equal to the value of mu naught by 4 pi is 10 power minus 7. 10 power minus 7 into 2 into the current is 90 ampere. So 90 ampere divided by that distance is 1.5 meter. So this is equal to 1.5 meter. Now once again I will multiply and divide by 10, or I will multiply the numerator and denominator by 10 so that the denominator becomes 15 for easy calculation only. So B is now equal to, when I multiply this by 10, it becomes 10 power minus 6. So this is 10 power minus 6 into 2 into 90 divided by this 15. 1.5 into 10 becomes 15 because 90 is divisible by 15. So 15 into 6 is 90. So 15 into 6 is 90. So this is now equal to 2 into 6. So this is 2 into 6 multiplied by 10 power minus 6. So this is equal to 12 into 10 power minus 6, or B is equal to 1.2 into 10 power minus 5 Tesla. So the magnitude is 1.2 into 10 power minus 5 Tesla we have found. So here elimination method you can use. The option C and D can be eliminated, isn't it? Because the values are 2.6 into 10 power minus 5. We have got 1.2 into 10 power minus 5 Tesla. But option A and B both are having the same numerical value. Magnitude is the same, but direction. So how will you find the direction of the magnetic field due to a straight conductor? It is Maxwell's right hand rule, is it not? Maxwell's right hand corkscrew rule. So now you see that the conductor carries the current from east to west. So if you use this direction that is given by Maxwell's right hand rule means now for this the magnetic field should come out of the board, out of the plane of the paper. Understand? So option A is correct. It is perpendicular and outward to the plane of paper. So this is the option A is the right answer. Okay, fine. Hi students, Now the second MCQ. Two concentric circular coils of 1 turn each are situated in the same plane, that is vertical plane. Their radii are 2 meter and 4 meter, and they carry current of 0.2 ampere and 0.3 ampere respectively, but in opposite directions. That is, in one coil clockwise current means in the other coil anti-clockwise direction. Now the magnitude of the resultant magnetic field at the center, that is O, we have to find out. So one of the 4 options. First we will write the given quantities. So there are 2 circular coils, one smaller coil, the other one is the larger coil. Here 2 meter and 4 meter are their radii. So I will take the radius of the first coil. So this is the first coil and this is the second coil. The radius of the first coil I will take 2 meter, and the radius of the second coil is given as 4 meter. So this is 4 meter. The current flowing through the first coil, I will take this as I1 ampere respectively. So 0.2 ampere, this is 0.2 ampere, and 0.3 is the current flowing through the second coil. So this is 0.3 ampere. Now you see that the smaller coil is having the radius 2 meter and the larger coil is having a radius 4 meter. Now the current flowing in the smaller coil is in the anti-clockwise direction. So the current I1 here, this is the current I1, and current I2 is flowing in the clockwise direction. I1 is flowing in the anti-clockwise direction and I2 is flowing in the clockwise direction. So by using Maxwell's right hand rule, we can find out the direction of the magnetic field. Okay, first of all, magnitude of the magnetic field I will find out. So the first coil is carrying a current I1 equal to 0.2 ampere. So the magnetic field due to the first conductor, I will take it as B1. So this is equal to mu naught into I1 divided by 2 into R1. So B1 is equal to mu naught into I1 is equal to 0.2 ampere. So this is equal to 0.2 divided by 2 into now what is the radius of the first coil, that is 2 meter. So this is equal to 2 into 2. So this is now equal to mu naught into, I will multiply this 0.2 10 times. So this is mu naught divided by 2 into 10 is 20. So B1 is equal to mu naught divided by 20. Similarly, B2 I will find out. So here B2 is equal to mu naught into I2 divided by 2R2. Substituting the values of I2 and R2. Now B2 is equal to mu naught into the current I2 is 0.3. So this is equal to 0.3 divided by 2 into the radius is how much? Radius is what? 4 meter. So into 4. So this is now B2 is equal to, okay, this is equal to, I will multiply by 10 on both sides, so that this is 3 into mu naught divided by 80, 3 by 80 mu naught. So this is B2. Okay, now we have determined the magnitudes of the magnetic fields B1 and B2. Now the direction is given by right hand, Maxwell's right hand rule. You see that the current I1 is flowing in the anti-clockwise direction. Okay, anti-clockwise direction. Therefore, the magnetic field due to I1 should be outwards, pointing outwards perpendicular to the board. So this is outward. Okay, outward, perpendicular to the board. Okay, perpendicular to the plane of paper I will write. Similarly, here the clockwise current means the field is into the board. So here it is inward. Field B2 is inward, and that is perpendicular to the plane of the paper. Now we have to find the resultant field. No? At O there are two magnetic fields. One due to the smaller coil carrying current I1 and the other one is current I2 flowing in the larger coil. Therefore, net field, okay, the resultant magnetic field at the center O is given by BO. So this is equal to B1 minus B2. So I am going to substitute for B1, mu naught by 20. So this is mu naught divided by 20 minus 3 mu naught by 80. 3 mu naught divided by 80. The LCM is 80. So I will take the denominator as 80. So that 4 into 20. So this is 4 mu naught minus 3 mu naught divided by 80. So B is equal to, therefore resultant B at the center O is equal to mu naught divided by 80. So this is the final value of the resultant magnetic field at the center of the coils. So which option is correct here? Option B is mu naught by 80. Therefore option B is the correct answer. Option B is the correct answer. Have you understood? Okay, fine.